Hello, everyone. First of all, I would like to thank the organizers for giving me the opportunity to talk here today. I will be talking about the search of dark subhalos with gamma rays, and I will be doing so in a general perspective, leaving the details basically to the next talk that will be given by my student, Javier Conoronado-Blazquez, that will be basically talking about a couple of papers that we put recently on the topic, okay? Okay. Did I switch the slide? Can you see this?
Yes, we can see this is now.
Very good, very good. Okay. So let me start with an image like this one. This is a snapshot of a redshift 0 of an embodied cosmological simulation of a Milky Way size halo, by the way. This is in particular coming from the G-Halo simulation performed by Stadel and collaborators more than 1 decade ago. It has a superb resolution, more than almost 2 billion particles within the virial radius of the Milky Way, which basically allows you to go, to resolve very, very tiny stuff here. Just to put this figure into the general context and just to give you an idea about the scale involved here, let me overimpose also this sketch. As you all know, the luminous matter in the galaxy only is restricted to the innermost parts of the whole system. And then this luminous matter is surrounded by a huge amount of dark matter that we call basically dark matter halo, and that extends well beyond the radius of the luminous matter, basically a factor 10 or so. And also it has much more mass, also around a factor 10 or so, for instance, in the case of the Milky Way. Of course, the densities are much lower in any case. Okay, so something that you immediately can realize by looking at this figure is that the dark matter is not distributed smoothly, all over the place, but actually there's a lot of clumps here and there that we call subhalos if they lie within the virial radius, inside the virial radius of our system, of the Milky Way. And basically, this is what you expect in lambda CDM. The dark matter is basically not distributed homogeneously, but actually, given the way structure formation works, you expect all these subhalos, within bigger halos to exist. Indeed, in lambda CDM, what we get and basically what we believe is that the most massive of these subhalos will host the dwarf satellite galaxies that we observed today with our telescopes. While there should be still a huge population of smaller guys that would basically be not massive enough to retain gas or stars at all, and therefore they will remain completely dark to us. No? So we wouldn't be able to see them with our, basically with the typical wavelengths, optical or infrared and so on. And I will refer to this population of low mass subhalos as dark subhalos, because again, they wouldn't have a visible counterpart. Okay, so I will try to be a bit more quantitative about what I say, what I mean by dark satellites, dark subhalos, and what's the boundary between the luminous stuff and the dark stuff, right? And I would like to illustrate this point with this figure taken from a paper by Til Zavala and collaborators already a few years ago, where they basically showed the fraction of the halos that will become luminous in their simulation box at redshift 0 versus the mass of the halo that you consider. Okay, so what you can see, for instance, is that anything above 10 to the 10 solar masses should basically be visible to us, while this fraction of luminous stuff will be decreasing as you go down and down in masses, and actually below 10 to the 8 solar masses or so, you wouldn't expect the halos to shine at all. Again, because they wouldn't be massive enough. And well, there's also a few other mechanisms, but this is in principle what the main idea and what we expect, in lambda CDM too. So just to be a bit more concrete then, below these 10 to the 8 solar masses, or equivalently 8 kilometers per second for halos, all these halos will remain dark. But since I'm talking about subhalos in this talk, I will say, just to give at least a number to keep in mind, I will say, this scale where the boundary is between the dark and the visible lies somewhere even more down, just because subhalos can lose more or less 90% of the total mass due to tidal forces, and therefore, from 10 to the 8, I would say we can go more or less down to 10 to the 7 solar masses. So, in summary, any subhalo below 10 to the 7 solar masses is expected to be dark, and that's what I will assume for the rest of the talk. Okay, yes. Okay, so they are these tiny guys are totally dark. So how can we search for this stuff? No? There are a few approaches that people have been taking in the last few years. Here I will just highlight a couple of them that I think are very cool, and I also I prefer the most. So the first of them is the strong lensing. It's based on strong lensing. In this case, basically you look for flux anomalies in the lensing image, and by basically studying these tiny flux anomalies in this image, you are actually able to reconstruct or to infer the existence of subhalos in the lens, in the object that is acting as the lens. By using this technique, I would say pioneered more than 1 decade ago already by Simona Veghetti and others, and I also leave a few other references there. By using this technique, you can go down to prove subhalo masses more or less down to 10 to the 8, 10 to the 9 solar masses at present. And talking to these people recently, I will say it will be pretty hard to go below these masses. So it will be pretty hard to use this technique to, for instance, to test subhalo masses of 10 to the 6, 10 to the 7 solar masses. The second one, the second approach that I would like to highlight is the so-called stellar gaps. In this case, basically the study is based on stellar streams in the galaxy. So the idea here is that in lambda CDM, many of these subhalos, tiny subhalos, are very compact, right? And they will hit these stellar streams, creating some gaps between the stars. And basically, by applying very sophisticated statistical analysis on these stellar gaps, you can again infer the existence of subhalos as low as 10 to the 7, 10 to the 6 even, according to some authors, solar masses. Okay. Again, it will be probably very hard to go even below these masses, I would say, with this technique. And then the third technique that I would like to mention here, and I will be focusing for the rest of the talk, is the one based on gamma rays. Of course, the assumption here is that the dark matter is made of a particular candidate, is made of WIMPs, weakly interactive massive particles. And if this is the case, these guys will annihilate within the subhalos, and they will basically give you gamma rays. These gamma rays, of course, we can search for by using our instruments in the gamma ray regime. Interestingly, this may be the only way to prove subhalo masses below 10 to the 7 solar masses, provided that the subhalo is relatively, is close enough to the Earth. You can have a tiny subhalo, much lighter than this mass that I just mentioned, but that could be very, very close to us and still yield a very relevant annihilation flux, right? And also, more importantly, I would say, it will be probably the only subhalo search that will provide information about the ultimate nature of the dark matter particle itself. Of course, you will know, for instance, that this is a WIMP already, right? And also by studying the things like the spectrum of the source, you will end up by saying, what's the mass of this dark matter particle, of this WIMP, and so on. So it's a very powerful method, provided, of course, that that we are pointing to the right direction in terms of the underlying physics, right? Okay, so the idea, okay. So the idea that we have in mind is the following, so here in this plot I show you the annihilation luminosity versus the distance to the Earth for a sample of dwarf galaxies, both ultra-faint, the so-called ultra-faint galaxies, and classical dwarfs. In this case, basically, you have, I'm showing the J factor, the so-called J factor in the community, right? So it's a measure of the annihilation luminosity of these guys, as I said. So what we want to test is that if we should expect some of these dark subhalos to be very, very close to the Earth and still yield a very relevant annihilation flux that will be competitive and even higher, why not, to the ones expected from the dwarfs. If this is the case, there could be even more than one detectable subhalo. So this is something that we want to also to understand, right? How many basically of them could be potentially detectable already with our instruments, and even more than that if we have already detected them. And I will explain in a second why I'm saying this. Yes, so just about the general methodology that we use in order to search for dark subhalos with gamma rays, I will probably start by mentioning that around 1/3 of the sources that we have right now in the current catalogs, Fermilab catalogs, for instance, or gamma ray, any other gamma ray catalog, are unidentified sources. So this means we don't have a clue, an idea about what these guys are. Okay. And this is not a negligible number at all. So by talking, for instance, if we refer to the latest Fermilab catalog, we are talking about more than 2,000 sources that do not have a clear counterpart. Okay, so more than 2,000 unidentified sources. The citing possibility that I would like to emphasize here, of course, is that some of these 2,000 sources, identified sources, may be subhalos, actually relating to gammas and just awaiting for a proper classification, right? So what we do is to search for these potential dark subhalo candidates by identifying those NIDs that will be compatible with dark matter annihilation. And in order to do so, what we do is to build and to apply several filters based on the expected dark matter signal properties. So by doing that, basically we end up with a smaller list, no, compared to these more than 2,000 initial sources. The typical results that we have. Sorry, Fabio.
You just passed half the way, okay? You are like 3 minutes plus 5, 4 minutes plus 5, okay?
Okay, thank you. The typical results that we end up with by after applying this kind of filters and this methodology that I'm saying is the following. First, you have typically a few VIP candidates for which a dedicated data analysis or even follow-up campaigns with other wavelengths with other instruments can be done, of course. Then you also end up with a few more subhalo candidates that are compatible with dark matter, but probably marginally, and are still compatible with also other astrophysical emitters. Even if this is the case, I will show in a second in the next slide how you can use this information to set very competitive dark matter constraints. And finally, probably which is the reach of the method. If you are good enough and your filters are really are working very, very nicely, you may end up with a scenario in which no NID is compatible among the pool of NID sources that you have. And therefore, by doing that, by ending up in this way, you actually you will be able to put the best achievable constraints. So how do we do that? The idea is just to compare basically what we have, what we expect from predictions coming from embodied simulations and the observed gamma ray sky. Of course, from the embodied simulations, we can cook things like the dark subhalo factors, the number density, the spatial extension. And on the observational side, of course, we can also compute the instrumental sensitivity to dark matter annihilation, okay, in a precise way. And also, of course, we have the pool of NID sources in which basically we are going to look for dark stuff. No? So by confronting basically these two things, the predictions and the observed gamma ray sky, you end up with a number of predicted detectable subhalos, and you compare this with a number of NIDs that are compatible with dark matter annihilation according to your filters. By doing this comparison, you finally are able to set your dark matter constraints. Something important to notice here is that, of course, the less dark matter candidates that you have among the pool of NIDs, the better will be the constraints. Okay, so the better you are in rejecting NIDs from your initial list, the better will be the constraints in the end. Okay, so we applied all this methodology that I just mentioned successfully in a couple of papers that we submitted recently, and they are all accepted already. This will be basically described by Javier in the next talk. So I will basically skip this. This is just some publicity that we are actually able to set very, very competitive limits in these works. And again, Javier, I refer to Javier's talk for more details. Of course, we have not been the only ones that use this machinery. Okay, although I want to believe that we refined the whole thing, and I give basically a few other references, previous references in the bottom of the slide for your consideration. Okay, very briefly, I would like to emphasize how the embodied simulation work that we performed in parallel is very critical in order to reach robust constraints. As you can imagine, since these constraints are based on a comparison with the predictions that are cooked in embodied simulations, of course, the way you characterize the subhalo population in the embodied simulations is really critical. And this is something that we put a lot of effort on recently. Well, recently meaning more than 6-7 years already. So, for instance, we cook things like SWGO mass function, the SWGO radial distribution, the SWGO concentrations, and from there we basically connect all that. We go a step forward and connect everything with the gamma ray analysis and try to put, to envision the best observational strategy for us. Okay. And then finally, we'll also like to mention that there's, of course, a lot of open issues, in particular issues, some caveats that are still on the SWGO population. And there's a lack of knowledge on many things that I think are very relevant for us in the context of these gamma researches. In particular, just to mention a few ones, we still don't know the precise structural properties of the SWGOs at particular masses, in particular these low mass SWGO masses. Also, the SWGO survival down to redshift 0 is not obvious at the moment. There's a hot debate in the literature about it. So it's not clear that these tiny guys will survive until present time. And that's something actually we're working on already. Also, the role of baryons is not totally settled, I would say. In particular, these guys are expected to be relevant for the SWGO abundance and also the internal structure, indeed. So these are things that we are already looking at. And as I said, we have been working on for a few years now. And as I said, there's still more work that is needed, and actually we are doing already. So I will stay. You probably know more about this in the next years from us.
Miguel,
okay, so
total time. No.
Okay. So I have 5 minutes from the questions, right?
No. You are past your talk time, and you have in total 3 minutes, including the question. You're minus 2.
Okay, excellent, very good, thank you. Oof. Okay, so then I will skip the examples, the 2 examples that I have about the issues, and then I will leave you here with the future of the field from my perspective, from my point of view. Okay, so sorry for the delay then.
No problem. Unless there are questions, you can continue. I mean, you have in total still 3 more minutes. So let me thank you for until now. And so far I have received no questions, so you're free to speak more. I just wanted to.
Okay, I will just read then the future, the slide about the future. Okay, skipping the examples that I put, these 2 examples that I put about the caveats. Then I will focus only the future. Okay. So for the VIP candidates, we are already putting some observing proposals at all the wavelengths in order to shed further light on these few candidates that we have on the table. We're also building more refined filters for our analysis in order to reject NIDs that could be probably something else. In particular, we're putting a lot of effort on the spatial extension filters right now. Of course, we have in mind to extend our search to upcoming gamma ray catalogs. We're already working on that already. As I said, further numerical work is needed, and we are doing a lot of work on that in our group. And also, we are already trying to understand the capability of the future gamma ray facilities like CTA, like the Chelko telescope array in all this game. In particular, for instance, on the bottom right, you can see a plot with constraints, predictions for constraints for CTA. This is a work that will be basically hitting the archive within the next few weeks, so stay tuned. And finally, we're also exploring the use of new techniques like machine learning in order to disentangle between potential dark matter SWGO candidates and other type of sources, astrophysical or conventional sources. So again, stay tuned, and I hope I will talk more about this soon. Thank you so much.
Thank you very much, Miguel. So there are 2 questions that I'm going to ask for you, but maybe if it's going to be taken by Javier's talk, then. So one question is how and if the shape, the profile, so whether you have an FNFW or something else, affects the constraints. That's one question. And the other question is how one can set constraints on the size of the subhalo. So you have 1 minute to answer either one of the 2 or leave it. I guess Javier is going to present results for different profiles, so it's going to automatically answer the question, I suspect. Go ahead.
Yes, okay. So for the first one, actually, we're basing our studies on subhalo concentrations that were built in particular for NFWs, okay?
I will leave it to Javier, otherwise I don't want to apply different rules. So I will just leave it to Javier right now so that you are perfectly on time. We will start like 30 seconds later.
Okay, perfect. Yeah, I agree with that. Yes.
Thank you very much for your talk.
Yeah, thank you. Thank you, guys.
Javier, are you there?
Yes, I'm here.
On your screen, I'm going to give you a 10 minutes notice when you're off the way, okay?
Perfect, thank you. Okay, everything working?
Fairly well.
Yes, perfect. So thank you very much for the opportunity to present my work in this very beautiful workshop. Yes, my talk would be a natural continuation of Miguel's previous one. So I'm going to talk about how these dark subhalos can be actually detected, or maybe detected, with the Space Telescope of Fermilab to perform indirect dark matter detection. So straight to the point, this is the annihilation cookbook, the master formula we all work with. So we have here three main factors. We have first, this F is the gamma ray data, which accounts what do we see in the sky, in the gamma ray sky. Then we have the G factor, which accounts for is an astrophysical factor and accounts for how much dark matter we have and how is it distributed. And this point is critical also. And finally, the N gamma is a purely theoretical factor, a particle physics one, which accounts for the spectrum per annihilation. So how does dark matter annihilate from a particle physics point of view? So we'll talk briefly about the first one, gamma ray astrophysics. Currently, we have two types of observatories to observe this radiation. We have space and ground-based. Example of a ground-based telescope would be MAGIC, for example. We also will have, of course, the CTA, the Cherenkov Telescope Array, which is currently in construction. And both types, space and ground-based, are nicely complementary. And we will focus on the space-based Fermilab. So these are some specifications. The energy range is perfect to cover the WIMP dark matter searches. And I would like to stress out the extremely huge field of view of 2.4 stereoradians, which is, I think, 1/5 of the sky. So we can have a whole sky map every 3 hours. This allows to perform this kind of beautiful image. This is the 8-year operation Fermilab sky map in galactic coordinates. So you have here prominently the galactic plane and then lots of things around. This map can also be decomposed in many things. For instance, you have the galactic diffuse emission, which is a combination of non-thermal processes such as the inverse Compton, the Bremsstrahlung, and the pi-zero decay. And you also have point sources like the great vast majority of them are active galactic nuclei. And then you have also an isotropic non-resolved background of gamma ray sources. And the question is if we have dark matter hidden in this map. To understand this, we have to go to a G factor, which tells us where is this dark matter and how is it distributed. So this is a very similar picture to what Miguel showed before. The real radius of the Milky Way halo, dark matter halo, is much larger than the actual size of our galaxy. And therefore, the largest members of this subhalo population, this clumpy population, would host the dwarf satellites. Yet the smaller and closer ones, which are not heavy enough to retain any baryonic content and therefore to host any galaxy inside, may be excellent targets for dark matter detection. So how can we address this problem? Well, we take into account that depending on the assumed particle physics model, subhalos are expected to have masses to go down to 10 to the minus 12, 10 to the minus 6 solar masses. 10 to the minus 6 solar masses is roughly the mass of the Earth, so very small structures. The problem is that any simulation, any n-body simulation, is incomplete due to numerical resolution. And the problem is this is the subhalo mass function. This is telling you how many subhalos you have per unit of mass. And this is inversely proportional to the mass, meaning that as you go down and down in mass, you go up and up in the number of subhalos. And this at some point has to numerically diverge, of course. So we are using the Via Láctea 2 simulation, a very competitive dark matter only simulation from 2008, which resolution is 5 million solar masses. We cannot go below this number. So maybe we are losing something relevant with relevant J factor, relevant brightness below this limit, this mass resolution limit. And the answer is that we are actually, and we can account for it by characterizing the original simulation and using some lambda CDM recipes, semi-analytical recipes, to generate mock realizations of this simulation and push down the mass resolution limit to just 1,000 solar masses, so more than 3 orders of magnitude in mass, which is pretty impressive, actually. And this is the summary. On the y-axis, you have the J factor. This is the brightness of the source in gamma rays, somehow. The x-axis will be the distance to the Earth in kiloparsec, or to Fermi-Lat, of course. And the color code traces the mass of the subhalo. Therefore, you will have here the original Via Láctea 2 simulation will be just this top corner of the plot, while all these would be the repopulation we are performing. Likewise, you have these, some of these at least will be visible dwarf, well-known dwarf, because they are very, very massive. Yet all these would be dark satellites, completely invisible except in gamma rays if they annihilate. And the point, as Miguel mentioned already, is that these dark satellites are among the brightest subhalos. Actually, if you take a J factor, say 10 to the 19, for example, you have very well-known dwarf here with a very high J factor. And you have here dark satellites, which are at least competitive, if not even higher. So they have to be taken into account for sure in the limits. Now, as I mentioned, these dark subhalos are completely invisible. They don't host any baryonic content, and therefore they don't have any counterpart in any other wavelength than gamma rays due to dark matter annihilation. Therefore, if you take a look into the Fermi-Lat sky map I showed before, but now showing the type of, or the class of each source, you realize that 1/3 of the sources are unidentified sources. So maybe some of them are actually subhalos, if not all of them, some of them. The problem is that we are dealing with a huge pool of candidates and we want to reduce this number. To do so, we define some filters according to the expected dark matter emission from a subhalo, meaning that if something does not pass one of these filters, it cannot be a dark matter subhalo. It would be something else, we don't mind, but not a dark matter subhalo. I will not stop in all this, but I can say as an example, this third one is a flux variability filter. This is due to the fact that dark matter is expected to be very steadily annihilating into gamma rays. And therefore, one should not expect any variability of the flux over time. And therefore, if we observe this variability, we can automatically reject this source as a dark matter subhalo candidate. With this filtering, we can reduce very much our numbers. These, in this column here, are different catalogs of the Fermi-Lat collaboration. The 3FGL in particular is a very famous one, maybe you know it. And we have here the original number of unidentified sources, and here the NADs, or the sources which are compatible with dark matter after our filtering. In the case of the 3FGL, which has 1,000 of unidentified sources, the filtering is extremely efficient, and we end up with just 16. So it's very, very efficient. And oh yeah, I forgot this. We have to take into account also the lat sensitivity to dark matter subhalos. The sensitivity of the instrument is critical to set constraints, because if you want to set the typical constraints of the annihilation cross-section versus the mass of the particle, you will have here a flux, which is the flux you need to have a positive detection of the subhalo over the background, a 5 sigma detection. This has been traditionally taken as the threshold flux of the catalog. which is a first approximation, but is a very bad approximation actually, because there is an important dependence on these flags on the annihilation channel, the source sky position, and the catalog setup. Intuitively, we can see that a dark matter subhalo placed just here will require more flags to be detected. The instrument will be much less sensitive than one here, due to the fact that the diffuse emission is much larger and important here and here at high latitude node. We perform this by simulating lots of subhalos in the sky in different setups. The difference between these two plots is the catalog, but we can focus on the left-hand side, on the left plot. This is annihilating to BB bar in the 3FGL setup. This is the flags of the minimum flags required to have a detection, and this is the mass of the WIMP. And as you can see, going from very light WIMPs to very heavy WIMPs changes the flags of the detection by 2 orders of magnitude. So it's very, very important to take this into account. And as I said, a constant flags or a horizontal line here would be a very, very bad approximation. Now, once you have all these, you can perform a spectral analysis. Yes?
You're half the way.
Thank you. Thank you very much. So now you can perform a spectral analysis of the candidates. We have a short list of their 40 candidates in order to try to favor or disfavor the dark matter hypothesis. The advantage is that we have improved statistics. We have more years of lab data than the one reported on the catalogs. And we use the FermiPy software for this analysis. Basically, the idea is that for each of the sources, we are doing a point source detection map. This will be the source, clearly detected here. We model the region accordingly, and we compute the spectral energy distribution of the source. We try to fit it to dark matter, but also to traditional astrophysical models, which are typical of AGN, pulsars, etc., of other astrophysical sources, classes. And we work with 3 of them. First, power law, which is well known to the high energy physics community, which is a power law. Then we have a log parabolic model, which is a power law with a certain curvature, not very much. And finally, a super exponentially cutoff power law, which is typical of dark matter and also pulsars. And therefore, it's very difficult to disentangle between them. And we can compute the preference for dark matter by taking into account this generalized likelihood ratio test, where we have the traditional likelihood ratio test. These are the likelihoods of each models, but we also have another factor accounting for the difference of in the degrees of freedom of the models. And this delta TS we obtain, if it's positive, it means we have a preference for dark matter. So we would like to have at least a delta TS of 25 to say that we have a positive detection of dark matter, or at least a hint, a real hint of dark matter. Unfortunately, this is not the case at all. The 2 best candidates we have present a delta TF order 10, and this is not strong enough, and also this is pre-trials. We are not penalizing by trial factor, so the look elsewhere effect, so this would be actually even lower. Nevertheless, this having said this, if you take a look into the spectra, they follow very, very well the Fermi-Lat points. The line here with the uncertainty is the dark matter spectrum, the best fit spectrum, here annihilating to B quarks and here to the charm quarks. And as you can see, it follows very, very well the data of the Fermi-Lat. So yeah, preference, but not strong enough. As it's not strong enough, we can set constraints on the dark matter usual parameter space. This is sigma V versus the mass of the WIMP. The left plot is for the BB bar channel, the right plot for the tau plus, tau minus. And our constraints is the black solid line here. We are competitive with the Planck Cmb data and the traditional dwarf spheroidal constraints by the Fermi-Lat. And we are actually probing the annihilation cross-section, which is this dashed line, horizontal dashed line, which is a magical value, of course. So yeah, they are competitive and complementary, and more important, they are completely independent from each other. And just a note, the spectral analysis is actually improving the constraints a factor 4. If we did not perform any spectral analysis, which is in the first of the papers I mentioned, We can set constraints, but they will be a factor 4 weaker. So it's important to perform this analysis. And finally, I would like to talk a little bit about the spatial analysis. As Miguel said, we are doing a lot of work in this part. Why? Because over the years, there have been lots of claims, as you see here, that dark matter subhalos should appear as extended sources for the Fermi-LAT. And therefore, if you have an identified source annihilating with to a dark matter spectrum, fitting very well to a dark matter spectrum, and you also detect a spatial extension, it will be very difficult to be explained by other type of source rather than dark matter. So we go to our simulations first to check if this claim is correct. Here we have, again, the J factor, the brightness in gamma rays, and the x-axis is the angular extension, the angular size, integrated up to the scalar radius. And the color code, again, is the mass, although you see that there is no dependence at all with the mass. It's all mixed. And it's worth noting that these lines here are the point spread function of the instrument. This is somehow like conceiving this picture when you see clearly that these lights here are point-like, effectively point-like. Therefore, nevertheless, the background lights are somehow out of focus, and you cannot distinguish between a point-like or an extended source. Something like this is happening here. So at the left of these lines, you cannot distinguish between any actual extension or a point-like source. Nevertheless, on the right hand side here, you see that the brightest subhalos should appear as very extended sources for the LAT. So we can perform an analysis on our sources to say something, and unfortunately, all of them are completely point-like. We perform another likelihood ratio test, but for extension here over the point source model, and they are all completely point-like, so there is no hint of extension. Here is an identified source which is not well fitted to dark matter. Just as an example, here the likelihood increases, reaches a maximum, and then decreases. And this is an example of something actually extended.
Javier, your time, you have 3 minutes to the end of your question time.
Perfect. So I'm finishing. I need 1 minute more only. And we are not discarding, nevertheless, the source as dark matter subhalo according to this spatial extension, because we need a full work, which we are doing, and we hope it's on the archive 2 or 3 months from now, to fully understand how the LAT is sensitive or not to extended subhalos. And just a note, in this paper, we also did this as an entertainment, which is searching for the star streams with the Gaia data. If one of our NIDs is a source which is actually a dark matter subhalo, it may happen that is a strip dwarf spheroidal. And therefore, we can search in the field of each source of our best candidates for proper motions with Gaia data. And we actually found one source which is compatible with a stellar stream, but is spatially coincident with the Sagittarius stream. Therefore, we cannot say it's a Sagittarius stream. We cannot say it's another stream. We don't know what it is, but it's something interesting, at least. So I will leave now here my conclusions, and thank you very much, and I will take questions for 1 minute.
Thank you very much, Javier, for staying on time. We have something like 40 seconds for a quick question and a quick answer. But probably at this point, unless there is something extremely, extremely urgent, it's probably worth just reading the summary and conclusions, and not forget that there will be time during the breaks and a time for general discussion together with the members of the next workshop next week. I have not received any question. There was a generic question about machine learning to Miguel, but I guess that's going to take a very long time to discuss. So probably this is not the exact moment in time. So I would thank Javier and Miguel in the tandem again. Thank you very much. And Anastasia, are you there? You want to get set up?
Yeah.
Very well, I can see you.
Okay. Can you see my screen now?
And now I can see your screen. It's a beautiful color-coded signal. Okay, that was the timing saying that its time is over for them. That's perfect. Okay, I can see you. I will sort of interrupt you in 10 minutes from now to tell you that you're halfway, okay?
Okay, thank you.
Wow.
Thanks to all the organizers that you have this meeting, even though online, but it has the opportunity to connect all us together. So, as you heard from previous talks, we don't know, of course, what is dark matter. We are all curious about that, but it could be at any masses, and we don't know where exactly dark matter particle sits. And even more, we don't know whether it's only new particle or dark matter particle sits in some hidden sector, in some dark sector, and the only possible way to connect our world with dark matter particle is via mediators. So we don't know it as well, but what is important for us in this section that for indirect detection, dark matter could manifest not only via direct or via annihilation or decays, but also in some other ways that I'm going to describe here. And I will stop on two possible portals, dark portal and axion. And first I will start with dark photon. So dark photon is just a model where dark photon mixed with ordinary photons, and just phenomenologically it means that an ordinary photon could oscillate into dark photon and vice versa. And this oscillation is proportional to some coupling epsilon, and in the contrary of ordinary photons that are massless in the standard model, dark photons could be massive. And there are quite a lot of constraints on dark photon models, from accelerators, from space. And in this talk, I will consider this parameter space here. And as I mentioned, oscillations of ordinary photons into dark photons and vice versa is possible, but in a vacuum, the probability is very low. It's proportional to epsilon squared, to the coupling constant. And this coupling constant is very low. So this probability is quite low. But in the medium, one interesting effect happens that in the medium, we don't have massless photon. And in a medium, photon becomes effectively massive, and their mass is proportional to the square root of electron number density, or the charged particles. And it could happen that if the mass of dark photon is equal to the mass of ordinary photon, then you would enter into a resonance regime, and this probability of conversion becomes much larger than the coupling constant. So it's called the resonance conversion or resonance oscillations. And now we would like to answer the question where we have this conversion probability, where we have these oscillations. And this work was done with these people. And because effectively photon is massive, as I mentioned, and it means that its mass it's a square root of charged particles. And even though after the Cmb decoupling, our universe is almost neutral, but not exactly neutral, and the electron number density of free charges decreases as a cube with expansions. It means that the mass of dark photons, ordinary photons decreases as well. But then reionization happens, and it releases a lot of charges, and that's why the number density of electrons increases, as well as the effective mass of photons. Then at low redshifts, you start to have collapsed structures, and therefore your number density in clusters, so galaxies, is not equal as the average number density, and that's why you have a lot of spikes here. And if you want to have a resonance conversion, then you need to satisfy the conditions that the mass of dark photon is equal to the mass of ordinary photons. that means that you're sensitive only for these masses, relatively slow, because if you have very high mass, then you would not have any resonances, so you would not be sensitive. But for example, in this region, you would have 1,000 of resonances, and it means that there could happen a lot of conversion. And for example, if you take Cmb, a spectrum that is very well studied, and we know that Cmb is, to a very high precision, is a Planckian spectrum. And that means that if this Cmb photons would convert into axions, they would just disappear, and it will disturb the Planckian spectra. And in this way, you can put some strong constraints on this model. And Cmb is an all-sky survey, and when a Cmb photon propagates through space, it quite rarely happens that it will meet some galaxy or cluster. Our space is mainly in filaments. It's just intergalactic medium. And for example, at this plot, you see the size of galaxies. It just these small blue dots, and it's in 20 kiloparsec thickness. So you can imagine that when a light propagates, it will rarely meet these small dots. So basically, it propagates just into filamentary structures. But it's enough to have to create that photon gets some effective mass. As I mentioned, if we study Cmb spectra, then we would expect that it will change the Planckian spectra. And at this plot, you see this blue line, it shows the Planckian spectra, and these dots, it's data from FIRES. And at this plot, you can see that the deviation from the Planckian spectra is very, very small. So to a very high precision, Cmb is a Planckian spectrum. But if you have a conversion, then you would what you would observe here at Earth would not be a Planckian spectra, this one, but it will be multiplied by the conversion probability. So we will disturb the spectra, and from this we can put quite strong constraints on dark photons. And moreover, we can use the data from Planck, because we know that to a very high precision, Cmb is very isotropic, up to 10 to the minus 5. And it means that if you would remove some photons from Cmb, or you will add some more photons to Cmb, then you would add more anisotropy to this quantity. And in this case, you also can put some constraint. And as we showed, they give more or less more or less the same constraints. And but to put some constraints, we need to perform an all-sky survey as well, because this is done for all-sky survey. And for that, we use simulations. We use eagle simulations, and basically we extracted a random line of sight, and then we average the conversion probability and we put constraints. So we did it in these two works. And another approach people did, they used analytical approach, and basically we get more or less the same results in this approach using simulation and analytical approach. And here's some results. So at this plot, you see the constraints on the coupling constants with axion, with dark photon and ordinary photon epsilon, and this comes from Cobb FIRES. And this constraints from Pixie. It's a future experiment, and this lines is from Planck and SPT. And this was about dark photon. And we can even put more stronger constraints if you take into account small fluctuations and small scales, because we add this additional conversion at small scales, and that's why if we will not study the whole Hankin spectrum, but parts where we're sensitive, then we can improve even further our constraints. But at this point, that's what we have. And if you assume that your dark matter particles is made from axions, and this model was studied to explain the edges anomaly, and the parameter space that explain the edges anomaly is here with this blue line. And with this approach, we are able to exclude quite a large parameter space for this model. Yeah. Now,
sorry to interrupt. You're a bit past your half total time. Okay, so you have 4 + 5.
Yeah. Thanks. Now I would come to axions. Why we consider axions here? Because what I just talked about dark photons is very similar with this case for axions. And now I will explain in which way. So axions, again, as dark photons, they could convert into photons, but they can do it only in the presence of magnetic fields. So that's one important difference between these two models. But it's very similar to what we just discussed. So of course you need to change the mass of dark photons to the mass of axions, but the coupling constant changes quite in a straightforward way. So you have this time you have an energy dependent coupling constant G, and this conversion can happen only in the magnetic field. So now you would have the effective coupling that is proportional to the magnetic fields, and also is proportional to the energy. So that's the main important difference between axions and dark photon. But if you would make these changes, then you can get a very similar formula for the conversion probability of axions into photons. Now it's proportional to energy, so it's energy dependent, and it's also proportional to the magnetic field squared. So with higher magnetic fields, you have higher probability of conversion. But the rest is the same. You need to satisfy the condition where the effective mass of axion is equal to the effective when the effective the effective mass of photon is equal to the mass of axions, and it could happen only in the magnetic fields. And this work was done with these people, and here what we have. So we use Illustris TNG simulation. Again, we need the electron number density, and you can see it here. But on top of that, we need the magnetic fields, and Illustris TNGs describe magnetic fields quite in a good way. And at this plot, you see the magnetic fields for the same snapshot and the metallicity. You can notice here that in fact metallicity, what astronomers call metallicity, is everything that is heavier than helium. So metallicity is those particles that were in supernova explosion. So they trace the magnetic fields much better, because the magnetic fields they were produced in collapsed structures and they just blow away. And that was what you see here. Because, for example, if you take like this part, you see a strong magnetic field here, relatively strong. That it's as strong as in clusters, but at this plot you don't see any structures, any strong electron number density. So that is why, like, this part is a bit confusing at the first glance, because you expect to have strong magnetic fields in the places where you have structures. Otherwise, who will produce them? But at this plot with metallicity, you see thumb traces. So metallicity trace magnetic fields better than electron number density.
Anastasia, past your time, so now you have 5 minutes for the question.
Yeah, I'll finish in a few
certainly use it for your talk, as usual.
Yeah.
It's just...
So here we show the same bubble that is mysterious here. And we zoom in it, and we show the magnetic fields where we show the virial radius of halos. So it's very small, in fact, and the strong magnetic fields outside the virial radius is really large, and this box is like 10 to 15 megaparsecs. So the magnetic fields that were created in these small structures outside these structures are quite strong, and they're long. And these magnetic fields were produced by supernovas and by black holes. And yeah, actually, they're quite hard to detect, because to detect them with, for example, Faraday rotation measure, you would need quite large electron number density, but the electron number density here is quite low. And the same is true for temperature. So they're not real to be detected. And for gamma ray astronomy, for example, it's quite important, because when you propagate, it could happen that, for example, here we checked that it's pass through relatively large magnetic fields for quite a long of the line of sight. And for example, more than 50 random line of sights, they pass strong magnetic fields more than 10% of their length. So it's important to take into account for gamma ray astronomy, for example, and radio astronomy. And here's the result. Unfortunately, in comparison with dark photon, the results from intergalactic magnetic fields with CMB is not strong compared to other constraints. And to improve them, we need to go to higher energies, but we don't have so well-studied sources there. That's a problem. So I will come to my conclusions. So our universe is not empty, and it fills with filamentous structures that could make photon massive, and with outflow from magnetic fields. And it could give us the opportunity to check our models and put some constraints. Thank you.
Thank you very much, Anastasia, for being perfectly on time. So we still have some time for questions. If there's any question for Anastasia. Okay, so I have a question for you. You said you calibrated, or you obtained your results through simulations, right? So you had to use a simulation of big structures that you took from Eagle or Illustris TNG, I'm sorry?
Yes. For dark photons, we use Eagle, and for accents, we use Illustris TNG, because Eagle doesn't have magnetic fields yet. Okay,
but yeah, exactly. But you didn't do this in the case of scenarios with warm dark matter. So I understand the question is completely offside, but
no, we didn't work with warm dark matter, no.
Because you're sensitive to what's the size of the structures you're sensitive to?
Well, we're not sensitive to very small structures. Like the difference between cold dark matter and warm dark matter, it's on relatively small scales, but
yeah, exactly. So I guess the question is, you are sensitive to way bigger scales. So you.
Yeah.
I understand. And when you're mentioning the impact on gamma ray astronomy, you're talking about the possibility of possibility to see magnetic fields through AGN or Blazer in AGN or Blazer spectra, or? Well,
for example, some people want to constrain intergalactic magnetic fields using TV sources, and that's what is, for example, it can be done with CTA, and for that. You would like to measure the magnetic fields in voids and not the contribution from galaxies. For example, that's one possible direction. And another one, when you consider the propagation of TV photon and Again, if you're talking about axion, then the contribution of bubbles also could be important because it has quite a large space where you have quite strong magnetic fields.
Okay, I see. Thank you very much, Anastasia. If there is no other question for Anastasia, 1, 2, and 3, we are perfectly on time for Elena's talk. Thank you again, Anastasia. Elena, can you get set up?
Yes, I share my screen.
I can see you at the moment. I cannot see your screen. I think I'm about to see your screen.
Now, in principle, you okay? Great. I just take the laser pointer.
If you can check the chat, but I will interrupt you in 10 minutes time. Okay, go ahead.
Okay. So I can start.
Please.
I think so. So hello, everybody. Thank you for the opportunity to talk about the integral X-ray constraints on subGeV dark matter, which we derived with Marco Cirelli and Nicola Fornengo, who are my 2 PhD advisors, and Bradley Kavanagh, who is currently a postdoc at the IFCA. And I also advertised that he will talk about dark matter and gravitational waves on Friday. So in the title, we write a subGeV dark matter. And just to fix an idea in mind, we mean dark matter particles with a mass between 1 MeV and 5 GeV. So the crucial idea of our analysis, of our work, is that subGeV dark matter can produce photons with an energy which is much lower with respect to the mass of the particles we are interested in. And this thanks to the inverse Compton scattering, as I will explain later on. And these photons fall in the energy range covered by the integral space telescope. Therefore, we can use the integral data in order to constrain subGeV dark matter. So in our analysis, we focused our attention on 3 annihilation channels: electron, muon, and pion. Each of them is kinematically open whenever the mass m(chi) of the dark matter particle is above the mass of the electron, the muon, or the pion, depending on the channel under study. The total flux that we observe with our telescope is the sum of 3 main contributions. Which one? Final state radiation, radiative decay, and inverse Compton scattering. So let's take, for instance, 2 dark matter particles which annihilate into muons. They can radiate a photon, and this is the so-called final state radiation. But they can also decay, and the W boson or the positron can radiate a photon as well. And this is the radiative decay emission. Final state radiation and radiative emission made the so-called prompt components. And then we have the secondary components, which is the inverse Compton scattering, on which I will say some more words in a minute. So the differential flux of the final state radiation has a very well-known expression. So there is a dependence on the particle properties, mass, and annihilation cross-section. Then we need to take into account also the energy spectrum per annihilation event. And finally, if we look in a certain direction theta in the sky, we observe all the photons coming around the line of sight. And therefore, we need to include also the so-called J factor, which is the integral over the line of sight of the squared dark matter density distribution. Squared because in our analysis, we consider annihilating dark matter. And we use an NFW dark matter profile. For the muon and the pion channel, we have also the radiative contribution. The expression for the differential flux is the same of the final state radiation. We just need to replace the energy spectrum with the proper one. Now, coming to the protagonist of our work, which is the inverse Compton scattering, let me quickly recall the physical process under consideration. So we have dark matter particles everywhere in our galactic halo. They can annihilate and produce pairs of electrons and positrons. These electrons and positrons can propagate and they emit the ambient photons in our galaxy. In our analysis, we consider 3 kinds of low energy radiation fields in our galaxy: Cmb, infrared light from dust, and optical starlight. And as you already know, in the inverse Compton scattering, we have the electron that interacts with the low energy photon and transfers part of its kinetic energy to these photons. Therefore, the final photon will have a higher final energy. In particular, the final energy of the photon can be approximated as 4 gamma square is 0, where 0 is the initial energy of the radiation field, and the factor gamma is simply the Lorentz factor, so the ratio between the initial energy of the electron and the mass of the electron itself. So, as I said at the beginning, we want to study subGeV and few GeV Darmet. So we expect that they would produce electrons with an energy, for instance, in this third column. So let's take, for example, a 5 GeV electrons, which scatter off a Cmb photon. And this can produce a final photon with an energy of 40 keV. Similarly, a 0.5 GeV electron, which interacts with an infrared photon, will produce a final photon with an energy of 40 keV. But we may consider lighter Darmetzer particles, which may produce an electron with an energy of 50 MeV. This can do inverse quantum scattering with optical photons and produce a final photon with an energy of 400 keV. So as you can see, after the inverse quantum scattering with these sub-GeV electrons, these low energy radiation fields become hard X-rays and soft gamma rays. And these energies are covered by the integral data. So, as I have anticipated, in our analysis, we used the data of the Integral Space Telescope, which is an ESA mission that took measurements between 2003 and 2009. And it covers an energy window between 20 keV and few MeV. So basically, hard X-rays and soft gamma rays. The integral data are provided in two different forms. They are provided as an energy spectrum in a rectangular region, which includes also the galactic center. And in this slide, I show you the photon spectra, so the energy flux as a function of the final photon energy for two different cases, in order to point out and to stress on how the three different components, final state radiation, radiative decay, and inverse quantum scattering, contribute to the total X-ray flux. In the left panel, we have the case of Darmetzer particles with a mass of 150 MeV, which annihilates into muons. They can produce gamma rays, which fall shortly before the Fermi data, but they can also produce a signal in X-rays, which fall precisely in the energy window covered by the Integral Space Telescope. And let me also point out that both the final state radiation and the radiative decay, in this case, pass well below the integral data, and they are several orders of magnitude smaller with respect to the inverse quantum signal. Therefore, considering the inverse quantum component in this case is crucial, since it is the leading contribution to the total, and therefore it will bring to stronger constraints. On the right panel, we have the case of Darmetzer particles with a mass of 10 MeV, which annihilates into pairs of electrons and positons. And instead, this case is better constrained by the final state radiation. Why? The reason is that the inverse quantum component becomes important, becomes a dominant term at energies much lower with respect to the energy window covered by the integral data. And this will be relevant at the end of my talk when I will present our results, our bounds. But the integral data are also provided as an angular flux latitude beams. And these are actually the data that we used in our analysis. So this dataset is divided into 5 different energy bands from 27 keV to 1.8 MeV. Each of these energy bands includes 21 beams in latitude and refers to a longitude window between -23 and +23 degrees, except the highest energy band, which includes only 15 latitude beams and refers to a larger longitude window. So in this plot, I show you the angular profile. In particular, I show you the angular profile in the energy band between 100 and 200 keV. The green points refers to the integral data, while the black points refers to our theoretical prediction that we estimated for Darmetzer particles with a mass of 150 MeV, which annihilates into muons. So what are the interesting features in this plot? We can say that the Darmetzer angular profile becomes larger as we approach the central latitude beams. But this is not surprising, since the Darmetzer density is higher as we approach the galactic plane. But you may have noticed that the very central latitude beams is much smaller with respect to the neighboring ones. And this is due to the fact that the very central latitude beam corresponds to line of sight which cross the galactic center. where we have a higher gas density, and therefore we expect that our electrons and positons lose energy in other ways, and so the inverse Compton signal is suppressed. In our analysis, we focused our attention on the high latitude beams, and we mask these central beams in the gray region.
Elena, you are half the way.
Okay.
You're half the way now.
Okay. So in this slide, I show you the angular profiles in 4 out of the 5 energy bands that we considered. So the color points refers to the data that we use in our analysis to derive the constraints, while the black points refers to the theoretical prediction that we derived for dark matter particles with a mass of 150 MeV, annihilation cross-section of the bound, and the muon channel. So some of you may be curious to see the bounds that we obtain in the 5 different energy bands. On the first panel, so on the left panel, I show you the muon channel, while on the right panel, there is the electron channel. Most of the time, the strongest constraints come from the 4990 keV energy band, while the weakest constraints come from the highest energy band. But what, in my opinion, is more interesting to show and to describe are the bounds that we obtain by considering separately the 3 different components to the total flux. So the solid line refers to the constraints that we obtain by considering only the inverse Compton signal, the dashed line only the radiative decay, and the dotted curves only the final state radiation. And as you see, when present, the inverse Compton scattering leads always to the best constraints on the velocity average annihilation cross-section for high dark matter masses. And this is due to the fact that for high dark matter masses, the inverse Compton scattering is the leading component to the total flux. But for low dark matter masses, let's say below 20 MeV, the velocity average annihilation cross-section is better constrained by the final state radiation. And this is due, if you remember when I show you the photon spectra, to the fact that the inverse Compton scattering for low dark matter masses becomes important with energies much lower with respect to the energy window covered by the integral telescope. And now we come to our final and main results, which are the overall 2 sigma constraints that we obtain by considering the total X-ray flux, so inverse Compton, radiative decay, by considering all the data points. So by combining all the 5 energy bands and by considering all the angular beams. And these are for the 3 channels that we consider in our analysis. We compare our results with the other existing constraints in the literature. In particular, in 2013, Essig et al. Derived their constraints on subGeV dark matter by considering several datasets from several experiments, including integral. But from the integral detectors, they use the other dataset, so the energy spectrum, which includes also the Galactic center. Among these 3 channels that we consider, they focus only on the electron channel, and they derive their bounds by considering the final state radiation. So they do not include the inverse Compton signal. And we see that after 40 MeV, including the inverse Compton component makes quite a significant difference and a significant improvement. Oh, it doesn't go, okay. So in 2011, the Voyager spacecraft crossed the heliosphere, and this allowed to measure the local flux of electrons and positons. And in 2017, Boudot et al. Derived their constraints on subGeV dark matter by using the data measured by the Voyager spacecraft. And they focused their attention on the electron and the muon channel, and they derived very interesting constraints between the dark matter masses between 7 MeV and 100 MeV. And finally, there are the Cmb constraints, which are of 2 types, S-wave and P-wave, for the electron and the muon channel. So if dark matter annihilation is speed independent, S-wave, the Cmb constraints are the strongest along the entire mass window of interest. But if dark matter annihilation is a P-wave, that is to say that it scales with the square of the velocity, in this case, these constraints becomes much weaker along the entire mass window of interest. So to summarize the main points of our analysis, we focus our attention on dark matter particles with a mass between 1 MeV and few GeV. The crucial point of our analysis is that we consider the inverse Compton scattering of the electrons and positons produced by dark matter particles over the low energy radiation fields in our galaxy, Cmb, infrared light, and optical starlight. After the inverse Compton scattering, these low energy radiation fields become X-rays, and this allows us to compare the X-ray data observed by the integral telescope with the theoretical prediction of the flux of the dark matter flux. We consider three channels, electron, muon, and pion, and if dark matter annihilation is a P-wave, we derive the strongest bounds in the literature at present time for dark matter masses between 150 MeV and 1.5 GeV. And with this, I conclude, and I thank all of you for your attention.
Elena, thank you very much for being on time and for the excellent talk. I already have a question by Aion, and it's perhaps I missed, but how did you treat the known sources, point-like, extended, and diffuse, seen by integral?
How did you treat? Sorry, didn't.
The known sources, the known sources, the sources that have been seen already by integral, extended and diffuse.
So actually, you mean also like the astrophysical source and all this stuff?
I don't mean, but maybe Aion, we have enough time for you to formulate the question yourself.
Oh, hi.
Yes.
Hi, Elena. Thanks for the very nice talk. Yeah, exactly that. I mean, Integral has seen a lot of sources, even in the galactic center. There is a known diffuse source of the astrophysical source. So how exactly did you do the analysis? Was it you who did the analysis, or you took the analysis already with all these sources excluded, treated, masked? How exactly was done the data analysis?
So okay, so we consider the data, these data of integral. Just you see also it's too small. Like this size is fine. You can see the integral data. Or do you want me to put it larger? I assume that it's fine.
Yeah, we can see it.
Okay, so we took the data by integral, and it's true that the integral collaboration also to modeling the astrophysical background, because we imagine that these are the diffusive, so X-rays observed by integral, and we imagine that we have an astrophysical background which is mainly due to the diffusive inverse Compton scattering due to the electrons and positons produced by astrophysical sources, I think, for instance, of supernovae. And we actually derive the bounds, the optimistic bounds, by considering also a modeling of the astrophysical sources, which is this, it's a preliminary result, this one. Of course, this will bring to stronger and better constraints. But in this plot that I show you, so here the solid lines, we derive our bounds, which are the conservative bounds, and so we imagine that the flux measured by integral is only due to dark matter particles. This makes our analysis more constraining, but of course, in a more realistic scenario, one should also consider the astrophysical background. But considering the astrophysics adds somehow some uncertainties related to the astrophysical modeling. I don't know if I answered to the question.
Thanks. Yeah.
Okay.
Answers.
Very good. Thank you very much. Is there any other question for Elena? Okay, then question one. Yes, you just need to count. Go, Miguel.
Yeah, sorry, because I put it on the chat, but maybe you didn't realize.
I didn't. Okay. Oh, yeah, sorry, you have one question. Yeah, go ahead. We have
no problem,
1 minute into it. Go quick, answer quick.
Okay, yeah, sure. So thank you, Elena, for the talk. I found it very interesting. I was wondering what's the main caveat in your bounds and how important this one can be.
So you mean some uncertainties, for instance, this is the...
Yes, the main source of uncertainty in your limits. So
this is actually an issue that we are computing and we are tackling during these days. So one of the more uncertainties, our highest uncertainties, is linked to the fact that we are considering an NFW profile. And in principle, one can use a Burkett profile or a more cusp profile. And we see that if we consider so different dark matter profiles, they affect our results. So a Burkett profile made the results a bit weaker, while a cusp profile make it a bit stronger. we see that one of our uncertainties is linked to the energy losses. So the energy losses depends mainly on the assumption that you made on the magnetic fields. So we use the energy losses as given by the PPCC, which gives you the possibility to choose among 3 different energy losses. We use in our in the results that I showed you before the MF1, but they also depend on the gas density that you consider. And we see that our results doesn't depend on the choice of the magnetic fields. This is not surprising because it affects mainly the synchrotron emission, but we see in the energy losses that this is very small. I can show you maybe here. So the synchrotron, the energy losses associated to the synchrotron emission are always, let's say, subdominant in the total energy losses, both on the galactic plane or outside of the galactic plane. So this is actually something that we somehow expected. But the energy losses depends also on the normalization of the gas. This slightly affects our bound, not so much. And there is also the normalization of the interstellar radiation fields. These also make a slightly difference in the bounds, but I have to say that the highest difference is linked to the assumption of the dark matter profiles. So just to show you 2 extreme cases, these are like the 2 extreme cases that you may.
Sorry, yeah, sorry. We can see the 2 extreme cases here. I'm sorry to interrupt you, but I have to pass on. So I guess the 2 different profiles are visible here. Thank you very much. I'm sorry to interrupt it, but otherwise we're.
No worries. By the way, if some of you have other questions, you can just email me.
No problem. Online and you can continue this. Thank you very much, Elena, again, and thank you. So, Aion, are you connected?
Yes, I'm already. Am I sharing my screen?
You are sharing your screen. I'm switching
full screen.
off. Sorry for that.
Okay.
And I will give you a notice 10 minutes from now. Okay, go ahead.
All right. So first of all, I'd like to thank the organizers for giving me the opportunity to talk about this interesting study that we've done in the beginning of this year about searching for dark matter in the galactic halo with this new instrument we are proposing to build called the Southern Wide Field Gamma Ray Observatory, SWGO. So here I will be talking mainly about very high energy gamma rays. So it's very important to we typically separate into high energy gamma rays, which is basically the GeV range, MEV GeV range, usually observed by satellites, and the very high energy gamma rays, which are usually detected by ground-based telescopes, such as atmospheric Cherenkov telescopes and air shower particle detectors. So the main principle behind is the following, is that if you have a gamma ray that reaches the Earth, this gamma ray will interact with the atmosphere and it will generate this shower of particles and Cherenkov light that will reach the ground. So if you want to detect these gamma rays, you will either put a detector above the atmosphere, so a satellite, such as the Fermi-LAT, but you can also put a detector of particles of this air shower at high altitude, so at 4 to 5 kilometers altitude, such as Hawk here on the left. Or you can actually put some telescopes at the ground or a little bit above the ground, 1,000 kilometers above the ground, to detect the Cherenkov light. And here is a very good example of this, such telescope, CTA. So what we are now proposing is actually to build a new wide-angle air shower particle detector in the southern hemisphere, complementary to CTA South. So it will be located at very high altitude in South America, and it will cover a very high energy range from a few hundred GeV to hundreds of TeV. And the idea is to have a significant improvement over Hawk. And there are various detectors concept currently under study. Now, there is some overlapping complementarity between all these different techniques. With the satellites, we actually have a very nice complementarity in energy. And with both the particle detectors and satellites, they both detect very wide fields areas in the sky. So they have field of views of the order of a few steradians. And with respect to IACTs, such as CTA, we actually observe more or less the same energy range. But there are some cons and pros between particle detectors and IACTs. I will start by the cons of particle detectors. They basically have a more modest energy resolution, poor angular resolution, also lower instantaneous sensitivity because the collection area typically is smaller than IACTs, and it has a higher energy threshold. So basically, it starts to observe after a few hundreds of GeV, although we are trying to push to really 100 GeV with SWGO. But IACTs currently, they can actually go to tens of GeV. Now, the pros of particle detectors is that since they observe the whole sky continuously, they can actually have a very accurate background estimation. They have a continuous monitoring of the sky, large aperture, like I said, of a few steradians. They have a very high energy reach, so they can go even beyond 100 TeV. And the data that is collected by these detectors, they can be used as archival data. Since you can see a huge fraction of the sky, you can actually later look at this data and see if you, for a future detection, if you actually have some counterpart in the archival data, such as it's done for Fermi-LET. Now, the southern gamma ray sky is a very interesting sky to observe gamma rays. We have the galactic center, we have the Fermi bubbles, we have most of the sources of the galactic plane actually seen in the southern hemisphere. And SWGO then would be complementary to all the particle detectors, such as Hawk and even LASSO that it's being built. Currently, it's already taken some data, but it's not finished yet. But SWGO basically will be a complementary detector to these northern hemisphere detectors. So there is a collaboration that was formed in July 2019, basically R&D collaboration with already 44 partners institutes from 12 countries and several supporting scientists from 9 more countries. And the main aim of the collaboration is the development over the next 3 years of a detailed proposal for the implementation of such an observatory, including site selection and the technology choice. That's where we are currently. The potential SWGO sites are basically over the Andes. The idea is to have a detector located above 4.7 kilometers to reach sub-TeV sensitivities. And here I give you a few examples of the potential sites. We have this very interesting Peruvian high altitude lake, Laguna Sibinacocha in Peru. And there are some actual studies being done to try to investigate this possibility of building actually detectors inside the lake, use the lake as our detector. There is this Bolivian site, the Alpaca site. There's a Cubic site in South Argentina, and there is this a site in Chile, in this Chajnantor region in Chile. Now, last year, early last year, there was a white paper that was produced where, in order to for science estimates, a white paper on science of SWGO, and in order to do this kind of studies, a straw man design of SWGO was developed, basically taking Hawk as a basis and increasing Hawk tenfold, taking an inner detector, very dense inner detector, and an outer detector a little bit more sparse. And here on the left, you can see the kind of sensitivity that we have, flux sensitivity, and we actually, within 5 years, it would be better than CTA above 10 TeV. Now, we already talked about indirect dark matter searches through gamma rays. I will go very quickly over the principles. If we have a dark matter self-annihilating with a rate which is proportional to the cross-section, the square density, and 1 over the square mass, this dark matter particle will annihilate, produce over some primary channels, and these will hadronize or decay over final channels, which are charged particles or gamma rays and neutrinos. Now, the charged particles, they will be basically cosmic rays. They will propagate diffusively in the galaxy due to magnetic fields. They will lose directionality, but we can still study them with the spectral signatures. Now, the advantage of gamma rays and neutrinos is that they do not deviate from their trajectory, so they point directly to the source. We can have both spectral and spatial signatures. Now, if we want to translate this rate into a flux, we have to introduce this the spectrum. Typically, we have different primary channels, and they typically have more or less the same features: a continuum with a cutoff of the particle mass energy, and sometimes you have this kind of bumps or line signals close to the dark matter particle mass. And we have to integrate the square density over the line of sight. This is what we call typically the J factor in the community. So we actually need a dark matter density profile model of the object you are observing, of course. Now, these normally come from either any-body numerical simulations. As we saw this morning, there's a lot of discussions over this CUSP profiles or chord profiles. Typically from observation of galaxy dynamics, we see some chord profiles. And here I give you the examples of the different profiles that fit the Milky Way density profile. And here I give you 2 examples of a Caspian and a chord, a Navarro-Franklin White, and an isothermal. And typically, in order to find these parameters, we need to use some tracers and dynamics. Now, especially for the Milky Way, this is extremely uncertain. You see that you have several orders of magnitude of uncertainty. If you take the J factor, you actually have even more orders of magnitude of uncertainty, especially close to the center. So typically what we do in this kind of indirect dark matter search is that we need to assume different profiles, and we normally choose extreme cases like a Caspian and a chord.
Aion, you're half the way.
Okay, thank you. Now we have several dark matter targets that we can look for annihilation or decay. I'll talk about decay a little bit later in the talk. I will not go through all of them since this talk will focus mainly on the galactic center, but we have the galactic center, we have dwarf galaxies of the Milky Way, we have galaxy clusters, and we have substructures of the galactic halo that we just heard Miguel and Javier talking about, but I will not talk about these specifically. I will focus on the galactic center. It is relatively close to us with a possible high dark matter concentration, of course, with this caveat of chord CUSP profiles, but it also has this problem of having a very high astrophysical background in them. Now, in order to estimate SWGO sensitivity to dark matter annihilation in the galactic halo, we focused our searches on the inner 10 degrees of the galaxy. 10 degrees is actually much more than IACTs can actually observe. They have a field of view normally of the order of 2.55 degrees radius. So SWGO actually could be able to probe this very large region. And the method we use is that we excluded this inner part of the galaxy, this band of 0.3 degrees plus minus, to avoid this very strong astrophysical background we have in the center of the galaxy. And we applied a 2D likelihood analysis using both spectral and spatial information in order to derive limits. We assume initially a NASTO profile. This has this advantage that a NASTO profile is very different from the expected background, hadronic and astrophysical background. So we can actually derive very strong limits with this kind of profiles. And this is the kind of sensitivities that we get with SWGO. In gray, you have SWGO. Here we have annihilation cross-section as a function of the dark matter particle mass. For the tau-tau channel. and everything above these lines we actually exclude. Here we also put CTA in red and LAT in predictions for LAT for 15 years of LAT and 60 new dwarf galaxies. And the very interesting aspect that we find is that first, SWGO, as you can see for the Tau channel, actually is more sensitive to CTA for masses above a few hundred of GeV. And one of very interesting aspects is that combined LAT, CTA, and SWGO, we can reach sensitivity smaller than the thermoradic cross-section for all masses below 100 TeV. Similar exclusions are found for W+, W- and BB bar. We also find that combined sensitivities are smaller than the thermoradic cross-section for all masses below 80 TeV for WW and 30 TeV for BB bar. We also study this effect of having a different dark matter halo profile. Here you can see in blue you have the AMASTO profile, and in red you have the bucket profile. Here you have CTA in dashed and SWGO in solid. So as you can see, the limits actually when you assume a chord profile, like a bucket profile, in case of SWGO, you do lose sensitivity, but you don't lose as much as a targeted IACT, such as CTA, because of the field of view. So these kind of wide field telescopes, gamma ray observatories, they are actually much more well suited for observation of chord profiles of the Milky Way. SWGO could observe chords as large as 2 kiloparsecs, or roughly a radius of 15 degrees in the sky. We also studied the case of decay. Basically, if you translate the annihilation into decay, the things that change is that now we have a rate which is proportional to the density, not the square density, and to 1 over the decay time and the mass. Now, the game is the same, so you have primary channels and then final states, and we are interested in the gamma rays. Now, these are the limits, the sensitivity that we get for SWGO, and as you can see, the limits are extremely powerful. We will reach unprecedented sensitivity looking at the.
I apologize for interrupting. You're 3 minutes from your total time, 3 minutes away from your total time, like you're -2 into your questions.
All right. I'm almost done. So basically, we also are better than CTA and Fermi-LAT for masses above 1 TeV, and we are much less sensitive to the change of dark matter halo profile, as you can see here in the solid and dashed line. So this is the kind of exclusions that we get. So here is the same for W+, W- and BB bar. And we will be pretty much complementary to CTA, although we can be better than CTA for certain masses. In order to detect the nature of this dark matter particle, if we detect it, we'll actually expect to be complementary to CTA, for example, confirming a cutoff or a line signal. Here I compare the rate of these different dark matter particle masses with the sensitivity in flux, and you can see that above 10 TeV, actually, SWGO would actually be detecting the cutoff or the line, whereas CTA would be able to detect the continuum. So we could actually confirm each other's detection of a dark matter particle mass. So basically, that's it. I showed here that with this future instrument, we'll be able to provide combined sensitivity with Fermi-LAT and CTA, able to probe dark matter cross sections for below the thermoradic value for masses below 100 TeV, 80 TeV, and 30 TeV for different channels. It's very well suited to observe core dark matter density profiles. We studied also dark matter decay. Will be complementary to CTA, and currently we are actually doing a future development looking at what is the sensitivity of this instrument for dwarf galaxies. So we have some preliminary studies which were done in the white paper, and now there are more ongoing studies with more realistic predictions. So that's it. Thank you.
Thank you very much, Aion. I have a question, but I'd rather wait if there's anybody who has another question. The question is related to the use of the dark matter profile in the Milky Way, which I didn't understand to which depth he went to the galactic center. At some point he had a slide. Like, but given that there is very little time to answer.
So what exactly was not understood? Like we assume
Yes,
both.
cores as larger as 2 kpc. So what you're saying is that if you have something spikier than 2 kpc, spikier than a core within 2 kpc, you will observe it.
Yes, of course, because if we have a flat, we need to be able to measure background, right? So we have a flat signal, we can't actually observe that.
Okay, very good. Thank you very much. So I think there's another question on one.
Yes, how are you?
Miguel, can you make it like a real quick, like 15 seconds for the question and then Aion 15 seconds for the answer? Yeah, counting.
I'll try.
No, then it's fine. It's fine. I will ask Aion offline. I raised my hand. You are not. You were not.
I didn't see. Sorry, I didn't see you. Should I say I apologize. I am a little bit tired. Human mistake.
No problem, Fabio. Of course. Yeah.
All right. I apologize about that. Let's get to Alfonso and the question. We can see you, Alfonso.
Do you see my presentation?
And I do see the slides, but they're not full screen, but we can see the slides.
And now?
They're not full screen, but we can see them. So either way, they're visible and we can get the information.
Okay, but do you see it full screen?
I saw it full screen for a split second, but I think it doesn't really matter as long as we can see the information content.
Okay, and it moves?
No.
We don't see it full screen.
We saw it for a split second, but what I'm saying is that it doesn't really matter as long as we see the information content.
No?
No, I think it's fine if you just.
Okay.
I think you should go to slide or to slideshow. You see on the top you have slideshow, and on the very top of everything.
Oh, sorry.
Slideshow. I think if you just click on the slide, it's going to be fine.
Yeah. Okay.
Yeah.
Oh, sorry.
I think it's just
I think, okay. Now it's better?
No, it's the same, but I think it's totally fine for everybody. We can see what. No, yeah.
Okay.
I think it's just go ahead.
Okay.
I think it's.
Okay, so thank you very much for the opportunity to give this talk. I'm going to talk from the side of the theory, and the idea is to give a short presentation about some models that can be of interest for indirect searches of dark matter. So I want to talk about non-abelian vectors in the dark sector, an opportunity for CTA and SWGO. And this is a work that is still in progress, and it has been done with the collaboration of Felipe Rojas Abate and Alexander Belayev. So I'm going to give some motivation for this work. I am going to present an ultraviolet complete model of dark matter and gauge interactions in the dark sector. I'm going to show preliminary results, and I'm going to pose the question: is it possible to discover or exclude this model? And later on, I'm going to state my conclusions. So, what's the motivation of this work? Well, the first one is to construct ultraviolet complete model for dark matter, which include non-abelian interactions in the dark sector. I mean, we are trying to model a dark sector which is complex in the sense that it has its own interactions. And this is important. We are trying to avoid that the dark matter and the standard sector interact via the hypercharge. So our proposal is very simple, is to add to the standard model a scalar field, which is a triplet of a new SU2 group. And the spectrum in the dark sector will be very similar to the low energy bosonic sector of QCD, which is composed by pions and the rho mesons. So this is the structure of the model. We have two groups.
So we're still seeing only the first slide. Huh? If you're making any reference, you're still seeing the Okay, good.
Now it's okay.
Now we are on a slide that sort of resembles what you're talking about. Yes.
No, okay. Okay, so this is the structure of the model. We have two groups, SU2, and the usual hypercharge U1 group. And we add a new scalar, this capital Phi, which plays the role of breaking these SU2 groups into the SU2 of the standard model. And we assume that all the standard particles, in particular the standard fermions, transforms under this group, and the usual Higgs doublet also transforms under this group. The second SU2 group is introduced only to provide interactions for a second scalar doublet, which is the dark doublet, which include this field H1, which is neutral and will be our dark matter candidate. Capital Phi and Phi1, both of them get a VEV, vacuum expectation value. The scale of the first VEV is called U, and the second one is called V as usual. And the A parameter is the ratio between those scales. And capital Phi include a neutral scalar, which we call sigma, and this will be important in the phenomenology of the model. Well, this is the relevant part of the Lagrangian of the bundle, but I will not bore you with these details. I will talk now about the preliminary result. I insist these results are preliminary, but I think that they can be important. Well, we compute the relic density for different values of the parameters. Here I'm showing you two plots which are representative of the parameter space. And the important thing is that we can saturate the relic density. We can reproduce the observed relic density for masses of the dark matter of the order of some TeV. I recall you that usually for models where the dark matter is a scalar, usually the relic density saturate at smaller masses, at smaller values of the mass. But for us, the saturation happened in the order of TeV masses, because the interaction, the internal interaction of the dark matter, the gauge interaction of the dark matter provides very efficient annihilation channels. So we need a heavy dark matter to reproduce the relic density. Okay. In the same region, we easily accommodate the constraint coming from direct searches of the dark matter. And here you have the limits imposed by xenon 1 ton, but our model for very representative values of the parameters can avoid these limits quite easily. Here I show you different projections of the parameter space for different values of the parameters. It is this one is important. Here we have the mass of the dark matter candidate and the mass of the dark gauge bosons, and you can see that in order to reproduce the relic density, we need heavy dark matter are also very heavy, of the order of 10 TeV gauge bosons.
So you're halfway your time. You're just
okay.
past 10 minutes.
Okay. Here I'm showing you the parameter space after all the constraints applied, including the saturation of the relic density. And again, we see that in order to saturate the relic density, we need a dark matter with masses between 1 and 10 TeV. And also we need a very heavy gauge bosons in the dark sector. Okay. So we have a dark matter candidate which can explain the observed relic density, which can avoid easily the constraints coming from direct searches. And I'm going to show you now that this kind of dark matter is very difficult to discover in collider, for instance, at the LHC, and even if in a 100 TeV collider, it would be very difficult to detect or to discover this model. Here, well, the easiest way to discover this model is producing the charge partners of the dark matter candidate. These charge partners are long-living particles. So it's they can be detected only as disappearing tracks inside the detector. So the detection depends on the lifetime of these charged partners. Here we have a plot which show you the lifetime and the mass of the charged partners, and all which is on the left of the lines, are excluded or may be excluded by the LHC. For our model, the lifetime of the charge partners of dark matter corresponds to the green area. So the important information in this plot is that, in principle, a collider like the LHC can exclude the charge partners for masses below 1 TeV. But for us, the area of interest, the region of interest, is above 1 TeV. So the message is that it is very difficult to discover this model in a collider for the region which is physically relevant, the region where we can reproduce the Rayleigh density. However, if we consider indirect detection, we have some chance. Here, we show you two plots for different values of the parameters, and our predictions of the cross-section relevant for indirect detection, and the constraint of coming from many observations, many experiments, including the expected limit coming from CTA. And in the relevant region, I mean above 1 TeV, CTA has the possibility, or will have the possibility, to observe a signal from this model, or at least exclude some of the parameter space. In the previous talk, we learned that SWGO will be complementary to CTA in this region and will have even a better sensitivity. So SWGO also have an opportunity to discover or to disprove this this model. So
Alfonso,
no, this is my last slide. So in conclusion, the vector resonance in this kind of model, I mean, in this fabulous model with gauge interactions in the dark sector, the vector resonance provide efficient annihilation channels for the dark matter. So this fact push the mass of the dark matter to the TeV region in order to satisfy the observed Rayleigh density. But it's difficult to discover the dark certain in colliders and direct detection in this range of masses. But indirect detection, in particular CTA and SWGO, has a chance. So this is the main message of this talk, that indirect detection can be the only possibility of discovering this kind of model. Thank you very much.
Thank you.
Thank you very much, Alfonso, for being perfectly on time. Still have 1 or 2 minutes for questions to close it in time. Questions?
Fabio, I have a question.
Go, Enrico, please.
So thanks, Alfonso. So my question is, how do you explain this possible efficiency of indirect detection searches over direct detection? Because I understand that the mass suppresses the signal for colliders and indirect detections, but I don't really understand why indirect detection is not as much as affected.
Well, this is a good good question. In our results, I mean, for some values of our parameters, for instance, this is very small. This alpha 1, I think that is our relevant coupling constant here, and alpha 1 is the mixing between the Higgs boson and the dark matter. Our predicted cross section can be very small. In this model, the only interaction between the only interaction relevant for direct detection between the dark matter and the standard sector is through the interchange of a Higgs boson, and this is very small, and this can be very small in our model, naturally very small, and also our dark matter candidate is very massive. So these two facts conspirate in order to give a small cross section relevant for direct detection.
And the same doesn't happen for indirect detection.
No, because indirect detection has additional contribution. In particular, the annihilation for let me see, the annihilation can be mediated by this sigma scalar, which can be heavy, but it couples strongly enough to dark matter, as well as the resonances of the SU2, SU2 are can couple strongly enough to dark matter to provide annihilation that can be detected by indirect searches.
Okay, I see. Thanks
I
a lot.
apologize, but I have to. I find this fascinating, and in fact, I think Maria is going to show something that on the third day that it goes and it's very close to the constraints that you're inferring. But I think we're at the point where we should stop and thank Alfonso and all the other speakers of this session again. If you want to switch your camera on altogether, like we did for the previous session, if you're still there. And Aion, Yvonne, I don't know if Miguel, Javier, and the speakers of the session are online. Well, no, okay, I cannot see you. That doesn't matter. I just want to thank everybody again. And I don't know what time is in your time zone. It's 9:20 in continental Europe. And I think it's a good moment to stop. So thank you all once again for the beautiful day. We're gonna have a similarly exciting day tomorrow, I hope. And I will see you tomorrow. Tomorrow we start at 9 a.m. Brasilia time, which means 1 p.m. Time in Central Europe, and you can convert it to your own time zone. It's 1 hour earlier than today. Let's put it this way. And I'll see you tomorrow. Thank you very much all.